Okay, good morning, everybody. I'm Ben Rowley, and I will talk you through large language models this morning. We will have an introduction to what they are, how we've arrived at this point in time, and kind of a high-level overview of how they are used to generate text, what's actually happening inside. So we'll work through this step by step, and then we'll take some questions. If any of you have questions, I hope I can answer all of your questions. And then after that, I will very briefly demonstrate how I will deploy a large language model in the Microsoft Azure cloud, and how I will then connect that to a Java Spring Boot application from scratch, just like that. So let's begin with an overview of what is a large language model. So a large language model could be loosely defined as an artificial intelligence model that's designed to understand and generate human language. Characteristics of it are that it's trained on a huge data set, which we may consider slightly controversial. I know some quite famous authors have been upset that perhaps their work has been used, but nevertheless, a very large body of text data is used to train these models. They're capable of various natural language processing tasks, text generation being one, text summarization being another. And some examples might be GPT, Gemini, or Claude, Mistral, Mixtral. Right now, there are a lot. It seems like every week or two, there are more. So this is an exploding technology right now. So what do we mean by GPT? What is a GPT? Well, the letters themselves stand for generative pre-trained transformer. So the generative part indicates that something is generated. So for what I will mostly work through today is how text is generated, but we all know now that images could be generated, audio could be generated, video could be generated. The P for pre-trained, I think, is the really important part for us as software developers, software engineers, because this really makes an AI model an out-of-the-box tool that's ready for us to use, in much the same way that we can use an SQL database, or we might use a front-end framework like Angular to help us develop applications. Now we actually have an artificial intelligence as another tool that we can bring into our application. Whilst the models are pre-trained, they can be further fine-tuned. This is not something I've done. I have not fine-tuned or trained a model, but it is certainly a possibility. There may be some arguments as to whether or not that's a good idea for every use case, but we don't need to get into that now. The T stands for transformer, and this is the architecture that's at the heart of our current AI models that are being used everywhere. So they originate from a Google paper published in 2017 called Attention is All You Need. And this introduced what's known as the self-attention mechanism. So at this point, this was really when text generation, large language models, really began to generate cohesive output. I would say this is arguably the point at which they became genuinely useful tools. I would argue this is probably one of the most important scientific papers published in this century, when we think about the impact that it's had and the implications of it for us as engineers, but not just us as engineers, everybody everywhere, okay? I read in the news yesterday that now President Joe Biden has told the United Nations that they need to get on top of regulation of this because the world will change dramatically in the next 2 to 10 years. That's frightening on the one hand, but on the other hand, it's exciting because this is, I suppose we could argue that since the Industrial Revolution, people have feared for their jobs. Machines are coming from our jobs. Computers are coming from our jobs. But it never happened, and I don't think it's going to happen now. This is a new and super useful tool that is for us to learn and get on top of and see how we can integrate it into our work, into our lives, into our applications that we develop. But to really, really simply dumb it down and define what a GPT does, it's playing a game of what word comes next. The sky is blue, perhaps gray, just like today. So the key components of the large language model are the transformer. This is the backbone of the large language model. It consists of encoder and decoder layers. Within there, we have the self-attention mechanism. So this allows the model to focus its attentions on different parts of the input sequence, which, let's say it's a natural language text prompt. So your user or you yourself have typed something into, let's say, for example, the ChatGPT web application. I'm sure we've all used it. We type in some query and the model is able to focus on different parts of that input sequence. Positional encoding allows the model to know where each part of that belongs in this input sequence, because as the text is processed through the model, all tokens, which we'll learn about in a moment, are processed in parallel, all at the same time. So without some kind of position encoding, the model has no idea where each token is in the sequence. We then also have the feed-forward neural network, which are used within the transformer layers to process information. And this is where you may have heard the term parameters. This is where these numerical values, which are learned through the model's training, are then applied to the current data set being passed through the model. So as previously mentioned, the transformer is a type of neural network architecture, which was introduced in the Attention is All You Need paper in 2017. Its purpose is to handle sequential data with the high efficiency and scalability, and it is the foundation of the state-of-the-art models that we now see. And I've said significance here, and I can't stress enough how significant this paper is to where we currently are with artificial intelligence. The components of the transformer are the encoder, which processes the input data and encodes it into context-aware representations. And this is what we mean by how a given word or subword, a token, has more meaning within a sentence or a paragraph. The decoder then generates the output based on the encoder's representations and the self-attention mechanism and the processes that have happened along the way. So the flow of this here will be the user input into the encoder, then we have our intermediate representation, then the decoder, and then finally we'll see our output. So the key features here are the positional encoding, without which the model doesn't know where each part of the text is, the self-attention mechanism, which really, for me, is the revolution here, and the feed-forward neural network. So if we begin with tokenization, we need to first break down the user input text into tokens. So the token we can imagine as a bridge between human language that we use and the numerical representations or vectors that the model processes. So here, if we see in this example, we've taken breaking down into tokens and we've broken it down. We've separated ing from break. It makes no sense to have a token for every verb and, taking the English language here, the progressive present tense of every verb. We don't need sitting and standing when we could just add ing to sit or stand. So there's an efficiency reason behind this. We can also see that some places we will break down just to a single character. Here we just have the S, which may be used to pluralize something in English. It may also be used to imply possession of an object, like Janine's laptop, for example. So also we see finally our punctuation mark or full stop or period. So the tokens can be words or subwords or just individual characters. The GPT-3 model from OpenAI has a vocabulary size of 50,257 tokens. So to put that in perspective, if you are a native English speaker and a graduate of university and you've studied a language-based degree, for example, history or law or English, you will probably have a vocabulary of around 100,000 words. English is a big language. The same person, but French, will have a vocabulary of around 20,000 words because French is a much smaller language. But what's really interesting here is that these 50,000 tokens must work for all of the languages that the AI model can speak or communicate in. So this gives you an idea of the efficiency here involved. So the GPT models use what's called byte pair encoding to break down the input text into tokens. So the initial tokenization will break the text down into its smallest units defined in the vocabulary. So usually starting with subwords or individual characters. But what it will also do is look for the largest possible string. Okay, so what is the longest string in the or piece of text in the input sequence that exists in the vocabulary of tokens? So the tokenizer will try to find this first. What this then results in is a sequence of token IDs, and this is used with what is effectively a lookup table. So the model then uses this sequence of IDs to find the relevant vector representation of that token, which we'll call an embedding, okay? So this lookup table of vectors and the corresponding tokens will have been defined as part of the initial training process and development of the model itself. So each model will have its own version of that thing. The vectors that are returned, by which everybody clear what a vector is, in 3 dimensions, a vector is a direction in space, right? So this way or that way or wherever. The OpenAI models use a vector of between 768 and 12,288 dimensions. That's hard to imagine as a human. Beyond 3, or maybe we had 4 in its time, but it's confusing. But it's still a direction in some kind of higher dimensional space. And this is really how semantic meaning is defined mathematically. So if we consider that this direction is yes, then it would make sense that that direction is no, because they are opposite. And if this direction is up and this is down, they are opposite. But it might be that this direction is fish and this direction is bicycle. And now, as they are perpendicular, they're unrelated to each other. But the vector embedding for woman and lady probably point in very similar directions. So this is how the model is able to determine semantic meaning. And again, this is something that will have been created through the initial training of the model when the model is trained on the large data sets. So the vector's job is to capture some semantic and syntactic meaning about the input tokens. But we then need the positional encoding. It's not enough to just have some semantic meaning for each token. Because all of the tokens are processed in parallel, this means that we need to know where each token is in the sequence. The model is not able to determine this and without a positional encoding. So again, embeddings and encodings being vectors, which are directions in some kind of higher dimensional space. The tokens which are close to each other in the input sequence will have similar direction. The tokens which are further apart, the first and the last word, for example, will be pointing in further different directions. So one more thing on tokens. It's important for us as developers using these large language models and implementing things to understand that tokens are money, effectively. If you have deployed a large language model in the cloud somewhere, then every token that is processed has some small cost to it. I think it's some small percentage of a cent in euros right now for each token. But if we consider that currently the GPT-4o model, when deployed in the Microsoft Azure cloud, currently that has a maximum amount of tokens of 128,000 on the input. That's a lot. If we consider that one token represents approximately 75% of a word in the English language, then let's say we have 100 words, that's 75 tokens. Or does it go the other way? 125 tokens. But you see how it adds up, okay? So if our output, the GPT-4o output is maximum 4,096 tokens. So it will not generate more than that. It can't. But we need to keep this in mind as developers. If we need to process a lot of text, that's expensive. If we have a lot of users that are asking a lot of questions, that's expensive. But again, there are these limits. And when we deploy a model, we can set constraints on this. We can restrict this. We can limit how many tokens are used for the input. We can also limit how many tokens are used on the output. The downside of this is that the model cannot start generating text knowing that I need to say what I want to say in 4,096 tokens, or let's say we've limited it to 500. It will generate text and then it will truncate. It will stop mid-sentence. Maybe some of you are developers here. If, like me, you've generated test data using ChatGPT, I'd use it sometimes to generate test data, generate some SQL insert statements for me. I will say, generate, let's say, 100 first name, second name, summer street address. It never gets to 100. And for a long time, I thought, this sucks. This model is rubbish. It's not working properly. That's not the problem. It's reached its token limit. It could never generate 100 for me. So this is important for us to understand as we start to use these things in our applications. Now, if we take a simple overview of the transformer architecture, we see on the left, we have our encoder, and on the right, we have our decoder. So let's imagine our data is flowing upwards through these models. We have first the self-attention layer, and then we have our feed-forward neural network. On the decoder side, we have our self-attention layer, and then we have encoder-decoder attention, followed by the feed-forward neural network. Also sometimes known as the multi-layer perceptron, which I think is a way cooler name, actually. The reason we have this additional layer in the middle of the decoder is because we want the decoder to only look at tokens that came before. So with our self-attention mechanism, we want to have every token gain something from the other tokens in the input sequence. What we don't want in the decoder is for the tokens to take something from future tokens. So each token will only look at what's come before. If we look now through the encoder in a bit more detail, we will see that the purpose of it is to convert our input sequences into a context-aware representation. So this means that each token wants to subtly change the numerical representation, the vectors, to gain some context from the other tokens in the sequence. But it also wants to let other tokens know something about itself. So this is what this self-attention mechanism is doing. That really every token is aware and learning from every other token. There are multiple identical layers, which each contain the self-attention mechanism, a feed-forward neural network, and then there are residual connections and layer normalization. In the GPT-3 models from OpenAI, there are between 12 and 96 layers, depending on the size of the model. So the biggest GPT-3 model has 96 layers. This model had 175 billion parameters. This is quite big. It's not been published how large the GPT-4 models are, but I think we can assume they are significantly larger, considering the leap forward they've taken and the ability, what these models can do. So our process here in the encoder, we are taking our input tokens and embedding them into their vectors and then adding the positional encodings. Then the self-attention mechanism processes the embedding. So each vector now is taking something from the other vectors. And this refines the meaning. A good example of this would be if I say, I can't find my keys. I don't know where I left them. Without some context, what does them mean in that sentence, right? So them is a pronoun, like it or they or whatever. It represents something. So for us as humans, this is easy to follow, but it's also easy to follow because I introduced a noun, an object, my keys, and then I referenced it using a pronoun. A pronoun, them. Okay, but for the AI model, it's really not good at that, or it historically was not good at that. What self-attention does is it allows this part of the string, the input text, them, to really figure out, oh, I am also keys in this instance, right? Them could represent anything, but in this case, it represents keys. So then we have our residual connections, which ensure our gradient flow. So this means that the original input is preserved across layers, and this helps maintain a strong contextual information. We'll see a more detailed model in a minute to show how that works. And then normalization ensures the layer's output is stable. So what this means is we do not want what we call the exploding or vanishing gradients. What this means is our numerical representations here, we want to adjust them by small amounts, because if we don't do this, then they very quickly can escalate and be wildly different, much higher numbers, or they can vanish down to almost nothing. So here we see a bit more about our position encoding. So our transformer takes our tokens. We've now got our vectors. We now need to apply a position encoding to each one so that they know where they are. And like I said, the transformer itself has no sense of token order because it's processing them all at the same time, all in parallel. So this is how we're able to inject some understanding about where each token is in the input sequence. And the positional encoding is usually done with either sinusoidal encoding or learned encodings. So the benefit of a sinusoidal encoding is that the cosine and sine functions are constant, right? Up and down. We know what that looks like, which means that the model doesn't really need to consider that in reference to the data set. But what our GPT models are using is a learned encoding. So this is learned during training. This gives them flexibility. So it allows the model to find the most useful way to represent information, and the model can decide what kind of positional relationship matters from the given data or the task. Then the integration with the language modeling, since the models are pre-trained on large and huge volume of data, these learn encodings can help it adapt to different linguistic patterns in textual data. This is more effective, really, than using the sinusoidal function. So there's a trade-off there. So here we see, in a bit more detail, the self-attention mechanism. So this is taken from the paper here. Is there a way I can hide this so we can see the whole screen? Does that?
You can move it simply.
Oh.
You can click the first one if you want.
Yeah, there we go. Okay, cool. All right, so here we see the scaled dot product attention mechanism is used in the multi-head attention blocks. Dot product is a matrix calculation in mathematics. We could probably imagine a matrix from mathematics as an array in programming terms, right? Let's say we now have two arrays or matrices of equal length. Let's take the first two values and multiply them together. Now we take the next first from one, first from the second. Now the second and the second, multiply them together. On we go. And then the result of each of those multiplications, we add together. This is our dot product calculation. So we see, starting at the bottom, again, we've got our inputs. Let's assume you've typed, tell me about schnitzel into ChatGPT. We then take our input embeddings, which we're going to tokenize. We're going to break our text apart. We're going to get our token IDs. Then we are going to find the relevant vectors. Then we will add our positional encoding, and then we're into the encoder block, where first we go to the multi-head attention. I see, one moment. Yeah. So into the multi-head attention. So this is the core mechanism of the attention layer. So it computes the attention scores based on the dot products of the query and the key and the value. So we will look at those in a moment, but these are derived from the input embeddings. So the multi-head attention, instead of performing a simple attention function, basically it takes this large vector space. Let's assume we're using the bigger one. I think I said it was 12,282 dimensions. It's breaking that into chunks. So this is why we have multiple heads. We're breaking down, each head within there is looking at a subset of this embedding space, this bigger vector space. After that, we have our add and normalization layer. So if we look here, what's interesting is we're feeding the actual input embeddings back in and adding them to the output here and normalizing them. And this is really what's helping us kind of maintain consistency throughout the model. It's stopping the numbers from escalating and then generating nonsense. It's kind of a stabilizing effect, I guess you would say. We then follow that with our feed-forward neural network. So this is where the parameters from the training process are applied to the tokens. So the same feed-forward neural network, the same set of parameters is applied individually to each token, or each, let's now think of it as a vector, and then we add and normalize again, and then we see we have our output embeddings. Okay, but we see up here, we can see we're feeding in, oops, I jumped ahead. We're feeding it back in here as well to add and normalize. So looking at the decoder stack, we see that it's similar. However, we've got the additional masked multi-head attention here. So this is where the model can only look at, or each token can only look at the previous tokens. When we're building our self-attention, we're kind of adding a little something from every token. We're only adding from the tokens that came before in this sense. And then we add in up here what's come from our encoding, our encoder again into our decoder. We then add and normalize them through the multi-head attention block, then back into the feed-forward neural network. To get to our output embedding, we've then got our linear layer, our final linear layer, and we've got our softmax algorithm. So what's happening at the end here is that we are taking our vectors and basically mapping them to a yet bigger vector space, typically 4 times the size. So let's say we had approximately 12,000. Now we've got a dimensionality of 48,000 dimensions on our vector. This is then in our linear layer. This goes to our softmax layer. And what softmax does is give us a probability distribution, which is what tells the model which token to pick next. Okay, so the softmax algorithm basically is then looking at all available tokens. So let's say we have a vocabulary of 10,000 tokens. We now need a representation from each of those and a probability distribution across them. We need to know what's the most likely next token here. And the way this is handled is that the outputs here are then through the softmax algorithm. The value of them all summed adds up to 1, and the range is from 0 to 1. Okay, so this is how we've now chosen, okay, that's the most likely one. The final step is to map it back onto an actual token, which is a character, a subword, perhaps a whole word. So why did we need the self-attention mechanism? I've been talking for now probably 20 minutes in English and nobody looks too confused. So clearly everybody can handle English and German here. Anybody who's struggled with these 2 languages from one direction or the other will understand that there are no one-to-one translations. Anybody who's had children living here but isn't a native German speaker has probably heard things like, "Can you me help?" You can't say that in English. You can, but it's not correct, right? So this was a problem for the people working at the Google Translate laboratory. And this is where the attention is all you need paper came from. They were looking to refine their translation algorithm. And German to English is particularly problematic, as you can see in this example. Can you me help this sentence to translate? I hope that sounds weird for you. It sounds weird for me, right? But in German, kannst du mir helfen, diesen Satz zu übersetzen? Well, that's correct, yeah? So what they were looking for is what they call long-range dependencies. How do these words relate to each other over a bigger distance through the string? So this is why and how we've arrived at this solution. So the purpose then of our self-attention mechanism is to allow the model to weigh the importance of different parts of the input string dynamically as we go through. Each token is going to gain a little bit of semantic contextual meaning from the other tokens within the context window. Context window meaning the string that we've typed in. We've taken, as we mentioned earlier, our query, key, and value vectors. So for each input token, we generate these 3 vectors. And the query represents what is this token looking for in other tokens, but how much attention should I give to other tokens? And then the key encodes information about each token, answering how relevant am I to the other tokens. And then the value contains the actual content or information of the token that's going to be passed on if it's relevant. This is really not a very mathematical explanation of how one might work with vectors. However, I did say it was going to be a high-level view. So I think this kind of, without taking a pencil and paper and starting to do calculations on a board here, I think this gives us a bit of an insight into what's actually happening, how this is working. So our attention scores are then calculated with the dot product of Q and K scaled by the square root of the dimension. So we talked about 12,000 and something dimensions, but remember, we're not working with all of that because we have multi-headed attention. So that's broken into chunks of smaller vector space, and then the scaling is the square root of that vector space. Then the softmax is applied to attain the attention weights. So this is really saying, okay, how important is it? Okay. And then the weighted sum computes the weighted sums of vectors using the attention weights. So here we can see that kind of visualized. As the model processes each word, the self-attention allows it to look at the other words in the input sequence for clues. So here we've got a pronoun, it. Could be anything, right? If just looked at in isolation, it could be the table or the projector or the sound thing up there or the light switch. But in this case, we see that, okay, the animal, see how these thicker, darker lines, it's taking more attention from those to the animal, not an animal, not any animal, but the implying the definite article, a specific animal. The animal didn't cross the street because it's the animal, not the street, was too tired. So it could reference street or animal. There's nothing else here that it could reference, but there's no way for the model to know without the self-attention mechanism. And I think this really shows why it's revolutionary, why it's really worked. So it allows the model to know how to understand everything within a given context. To the encoder and decoder differences. So the self-attention layers in the decoder operate in a different way. We've talked about how this is because we have what we call masked self-attention. So this is done by masking the future positions. So they're set to -infinity, basically, quite a low number, before the softmax step. So remember, the softmax takes all of these values and adds them together so that they add up to 1, but they all have a range from 0 to 1. If we've set all future tokens to -infinity, then they're effectively irrelevant here. They're way, way, way low numbers, 0, almost. So the encoder-decoder attention layer works just like multi-headed self-attention, except it creates query matrices, it's queries from the matrix layer below it. So if we go back again, we can see that here. So it's taken its vectors from here, from the output embedding. Where are we? Good. So, that was a lot of information. Here we see a quick visualization of masked self-attention. I think it's fairly clear what's happening here. Here we see that every token is taking something from every other token, but here it's only taking something from the tokens behind it. Okay. So then we have our final linear and softmax layer, which we see at the top here, which leads to our output probabilities. And so the decoder stack outputs a vector of floating point numbers. So we need to turn that into a word. And here we use the final linear layer followed by the softmax layer. So the linear layer is a fully connected neural network, and it projects the vector produced by the decoder stack into a much, much larger vector called the logits vector. So as I said before, if the model knows 10,000 English words learned from its training data set, then this would make the logits vector 10,000 cells wide, okay? Each cell corresponds to a unique word, or the score of a unique word. So this is how we interpret the output of the model, followed by the linear layer. The softmax layer then turns those scores into probabilities. So they're all positive, they all add up to 1, and the cell with the highest probability is chosen, and the word associated with it is produced as the output for this time step. So that's the much, much longer way of saying it's playing a game of what word comes next, right? The sky is, I don't know, full of aeroplanes, blue. Context is everything. Are you at the beach or are you at an air show, right? So it will change. This is really how we are doing it. Shall we take a moment for any questions that you might have? I hope I can answer any questions that you might have. If not, then I will go ahead and deploy a model and show you how we can actually do that. Yes.
Can you show the overview?
This guy.
Yes. Where does this output embedding come from?
This is. Let's look at the information here. So the output embedding from the decoder is processed. That's a good question, actually. It's shifted right. So I think it's the inputs shifted right. So we're taking our inputs and we're shifting them right as our output embedding, and then we have the masked multi-head attention. Okay. So what's happening is we've got our inputs and our, like, what's our user query? We're shifting them right onto our decoder. They also then, it needs its positional encoding, its tokenization, and so on. And then we have the masked multi-head attention. Then we're going here. This is all leading us up towards what word comes next. Yeah. So we're taking the same thing and we are basically doing, let me find it, this. So in the encoder, we did this. So in order to know what it refers to, or them, or they, or whatever refers to, we need the full context of the whole input. But for the output, it's proven to be, like, through the process of research. Not my research. I didn't make a large language model, but the smarter people than me over there at Google or Meta or wherever else, they have basically determined that, sorry, wrong way. They've determined that by taking this approach, they're able to develop or produce more consistent output ultimately. So, oops, I've gone the wrong way, one moment. When we look here, we've got our embeddings, which are then, it's the masked multi-head attention process. We then see that the output of this is added in again, right? But we see, you can see it looping around. So in much the same way that we looped our input around to add and normalize the output of the multi-head attention layer, and then that gets added and normalized after the feed forward layer. The similar thing is happening here. It's passed around, it's added and normalized, it's passed around, it's added and normalized. And so the reason this is really happening is to develop or to produce a consistent output, right? And to avoid what we would call the various gradient flow problems, the exploding gradient or the vanishing gradient. We don't want the numbers in here to go wildly to some different place. We just want to super subtly adjust them to extract meaning from them. I hope that answers your question reasonably well. Okay, shall we deploy a model? So here I am. But actually, before I do this, there's one step that I can't show you here. And that is what you must first do is I'm working here in the Microsoft Azure cloud to deploy a large language model, which I'm then going to connect to a Spring Boot application. Clearly, I have an Azure account. Well, not me personally, CIT has an Azure account, right? So that part of it, you need to create an account. You will need your billing information passed in. Obviously, I'm not going to put that in a video that's live on the internet. And what you also need is to actually ask permission to use an AI model, okay? So it's not just make an account and start using it immediately. There's a form to fill out where you need to let the good folks at Microsoft Azure know what your use case is. Why do you want to use an AI model? Okay, for us here, it was initially, I said that we are going to use it for prototyping and training and things like that. But now places where we've actually used it are customers who are using a model. When they then deploy their own instance, they will then need to apply to Microsoft and say, well, actually, we're using it with this application that might do X, Y, Z, whatever. So this step I won't show you, but once we are in and set up, we can deploy a model, which actually is frighteningly easy. So I'll come here and create a new resource, as we call it. I'm going to put it in my CIIT AI prototype resource group, and I need to choose a region. I'm going to use Sweden Central. And the reason for this is because not every region yet can deploy an AI model. There's, I guess, specific hardware that they need. I know that in Sweden Central, the GPT-4o models are deployable. I was previously using France Central, but you could only deploy GPT there, not the latest 4o model. That may have changed now, but if you look at the official Microsoft documentation on this, you can see very clearly which models are available where. Can anybody think of a reason why I've chosen somewhere in Europe? I hope this is obvious to everybody. Anybody want to have a guess? How is a server in the United States going to guarantee DSGVO or GDPR in English? It's not, right? They don't have the same laws. So by us deploying our model in central Sweden, we can be sure that Microsoft understands the implications of getting data security wrong. That's really, really expensive if you get that wrong. So we want to avoid that. So I'll put it in Sweden right now. I'll give it a name and I'll call it AI, what day is it? Thursday. I need to choose a pricing tier. There is only one, and then I hit the next button. I will make this available on all networks, including the internet. I will not give it any tags. And now it is preparing to deploy. Okay, now I can create that. And it is initializing my deployment. Once this has been deployed, I can now navigate to the deployment and deploy actual models within it. So, are we ready yet? Is it done? AI Thursday. There we go. So now we can go to the resource. Okay, here we can see, can everybody see that? Okay, yeah. So here I can see I can manage my endpoints, or I can view my endpoints. I can manage my API keys. So obviously, if I'm going to deploy something in a cloud, I want it to be somehow protected from everybody else. I want an API key. So if I now navigate to Azure OpenAI services, I can come now to deployments and I can deploy a model. I'm going to deploy a base model and I'm going to choose, let's go with GPT-4o, which is a chat completion model. I've chosen that. I need to, this model is not, oh, look at that. It's not available. That's interesting because yesterday it was available. Let's go with GPT-4 then.
As you said before, it's surprisingly easy.
Yeah, look at me. Look at me go. Okay. Why is it not available? Let's find out. I'll have one more try. Okay. And if it doesn't work, let's select again GPT-4o, deployment name. Let's call it chat model. Am I able to create this? Here I can choose how many tokens per minute are used, and here I have some content filtering. If you want to reduce the content filtering, you need to create your own custom filter. I can't think, there we go. I can't think of a reason why you would want to reduce the filtering in a deployed application unless you're working for law enforcement, for example. If you're working for the police and you're seeking specific language related to things that probably have no business being in a business office, then maybe you need to remove that filtering or have it reduced in some way. But anybody who's sticking an AI model in an enterprise application, I'm guessing you probably want all of the filtering to prevent anything untoward happening. So here we can see we've created a chat model, and I've called it chat model. It's GPT-4o model. If you want, we can do another one, super easy. Let's make an embedding model. Let's take text embedding Ada 2. We'll call this embedding model. And here we can see we're allowed more tokens per minute. Let's dial that back a little and we'll create that. Embedding models are used when we want to just embed data into the same vectors that are used by the model. So let's say, for example, we've got our own large body of text. We want to break that into chunks. We want the vector embeddings in that so that we can store that in a vector database. This allows us to then do similarity search, find similar text. This is kind of how the retrieval augmented generation pattern works. But yeah, for now we have one. So let's jump in. Let's create a new application in IntelliJ. We'll say new project. I will call it AI Thursday for consistency. I'm using Java 17. Okay. Now I'm going to choose to use Longbok. I want Spring Web. And I want from Spring AI, Asia Open AI. Is that everything that I need? No, I'll take the dev tools as well. Okay, good. Just like that, I have a Java application. So now if I come into my source code here, into main, I've got my application run. You can see that I've got no SDK. Oh, I have got an SDK set up already. Okay, good. We are good to go. So I now need to give my new application the relevant application properties. So that means I need Spring AI Asia OpenAI key. That I can take from my resource. So if I go, did I have that here? I did. Manage my keys. Here's my key. I will copy it. For those of you watching at home, of course, I will delete this model after the presentation so that we don't leave a model out there for free use for everybody. You're welcome, Mikhail and Katerina. Then we need our chat options deployment name. So this is the name that we've given our chat model in the cloud. I just called it chat model, right? So I come here and say chat model. Since I gave an embedding model, makes sense to put it in there as well. Let me check my spelling here. Did I spell it correctly? I believe I did spell it correctly. Okay. And then what am I missing? I'm missing my API endpoint, right? So that I can come back here and copy paste that from here. This is my endpoint, AI Thursday. Let's put that in. So now, all things being equal, my application ought to start. It does. So my application has started in 1 point something seconds, and I'm connected to my endpoint in the cloud. So we might as well do a quick test. So I'm going to basically, I'll come in here to my main folder, and I'm going to create a new Java class, and I'll call it AI controller. So I will just make a simple REST controller now so that I can send a query to it and see the response. And then we basically have a proof of concept, right? We prove that we can connect our model here. So let's go, we'll give the REST controller annotation. And I'm going to use the all-args constructor from Lombok because I'm too lazy to create a constructor here. So to begin with, I need a private final Asia OpenAI chat model, which let's call it chat model. And now I can go ahead and create a REST controller. So we'll say that this is a get mapping. With the value let's say ask. Now we will create a public. I'm going to return a map here. The reason I'm going to return a map is because This lets me extract what I want from the complete data set. I'm going to take just a specific chunk of it just to see what's generated. If I get the complete returned objects, then we see a massive information, which is beyond the scope of our, shall we call it, proof of concept here. So ask is then going to have a request parameter with the value message. That needs to be in those. And then I'm going to put in a default value. So here, this is just so that I don't have to type any text in later. I'm just going to basically ping this API endpoint with a default question built in. And let's say, tell me a joke about sausages. What am I missing here? A bracket, maybe? Oh, of course. That's what I'm missing here. Good. Then all I'm going to do is return a map of, and in here, I'm going to say generation. So I know that generation is one of the keys in the JSON that is returned from the model. So this is how I'm going to extract it. And then I'm going to say chat model call, and I'm going to pass in my message, which is a default message. Fingers crossed, Dr. Dowman, let's hope it works. I will restart my application then. And while that restarts, I will here in the test, I will create an HTTP request, which I'll call simply test. And now I can call get test. I can call my model. It's a get method and it's localhost 8080/AI ask. Am I missing anything here? Do I need my HTTPS? Let's find out. Sure, here's a sausage themed joke for you. Why did the sausage go to the party? Because it was the worst. Super. So proof of concept, we just deployed a model. We connected it to a Java Spring application. We just interacted with an AI model in a Java Spring application. I think that's really cool and exciting. So any questions about this point? Yes.
Wo hast du bei der Oberfläche ausgewählt, dass unten AI verwendet wird? Beim Deployment.
In OpenAsia, I'm in the, let me see here. I'm in the OpenAsia OpenAI studio. This is quite a clue that these are going to be OpenAI models, not Asia, not Meta or Olama or anything else, right? So if you come in here somewhere, oh, now we're talking, overview. Do we see it here? Explore and deploy. I think it's because I'm set up with Azure OpenAI. Basically, there are other possibilities. I think if you explore a little bit within the Azure user interface here, you can see quite a bit more of what's going on, what's available and stuff. There are other ones available, but obviously, I think Microsoft is one of the major investors in OpenAI, and yeah, they got dibs, as we say in English. They have the right to kind of deploy those models in their cloud and make them available and then make money from it, recoup their investment, I guess. Microsoft is going hard into AI. And another interesting news story I read this week is that Microsoft is buying out the 3 Mile Island nuclear power plant in America, scene of one of the most famous nuclear disasters ever, to provide enough power for its AI operations. So, this should give you an idea of how huge people expect AI to be in the coming year, 2 years, decade, thing like that. I don't believe the horror stories that AI is going to replace us all and, you know, we're all going to be living on universal basic income, or what do they call it here? Mindestsicherung or something like that. I just don't see it. It's a tool like anything else, right? Just like the internet was going to be the thing that took jobs, or the computer, or the Jacquard loom, or the steam engine. Like throughout history, there's a reason why everybody's going to lose their job to some new technology. But what happens is humans just become more efficient and do more cool stuff. So if this isn't a massive opportunity to do a whole bunch more cool stuff, then I don't know what is. Any further questions from anybody? Yeah.
Hast du hier jetzt wirklich ein eigenes OpenAI von der Instanz her laufen oder routen die das sozusagen nur weiter?
For those at home who didn't hear Bernhard's question, he's asking if I'm routing this further somewhere or if it really is my own instance. It's a private instance. So we deploy our own model for our own use case, and anybody who's got the endpoint and the API key can hit that. So if you're feeling charitable, you can of course deploy one and give the API key and endpoint to all of your friends and let them run up a huge bill. But in real life, you would deploy a model for your specific use case, and then you know that's just mine. It's an interesting point actually, because I've had a lot of conversations this year with not just other developers, but clients, people who are building applications, people that we at CIT build applications for regarding the deployment of AI or what we can offer them in terms of AI. And a lot of people are quite nervous about it. And I think a lot of it is coming from the data security aspects of it. What happens to our data when we send it off to a model somewhere in the cloud? And is this model learning from our data, then able to reproduce it somewhere? No, definitely not. The model is a static thing. You're taking a pre-trained existing model, putting it in the cloud with Microsoft Azure. I don't know who else you're going to trust. I mean, you could put it on the AWS cloud, you could put it on the Google cloud, you could put it in the Bundesrechenzentrum in town here. As of next week, I think you could put a model under the stairs here in the server in-house, because we'll start doing that here. But when you deploy here, you have the knowledge that, okay, Microsoft is a serious organization. They're going to take data security seriously. They know the implications of getting it wrong. I now have my own instance of a trained model that is used only for me. It's not learning from my data. It's not being developed further. If I want, I can use my private model I can develop that. I can fine tune that and somehow improve it. If I have the skills to do that, I don't. But let's say I wanted to go down that path. That is possible as well. You can fine tune your own model that you've deployed in the cloud. But is it your model? Yes. Is it secure? Absolutely yes. Are people going to be nervous about using it? Yeah, probably some people. But I see it as the new normal in a way. I don't see it as being any less secure than any other deployed web application, right? If you create a web application, you need to deploy that somewhere. Some organizations, let's say banks, government agencies, things like that, they will deploy their applications in-house on their own infrastructure. Perhaps it's even air-gapped, so it's not connectable from the outside world. And I understand that. However, doing this is no less secure than any other type of deployed web application. Yeah. So yes, to answer your question, it is your own model. Nobody else is using it. Okay. Yes.
Is this charge only per use, or does this have base cost? So if I program the client against the OpenAI API with an API key from OpenAI, this is not my own model, I understand this, everybody uses the same model. Are there some base costs? If I, as a private person, who wants to do the same thing, would this exhaust my budget, or could I afford it?
It depends how powerful of a power user you are. The question there, for those who didn't hear at home, are the costs involved. If we deploy our own model privately and we start using it, are there hidden costs? Are there anything we don't know? No, you pay per token. And that's visualized in, I don't know if I can see this here. Are you okay if I show the billing, like the costs incurred? No, I don't think you see anybody's. How do we see that here? I can't remember how we see it. All resources. Somewhere there's an overview in here where we can see all of what's been spent so far. So
what we can see is costs us, the prototypes in turn costs us only a few euros per month. So it is really, if you try to set up your own model and de-experiment a little bit, it's really just like, say, €5 or something like that.
So it's affordable for me at home.
Yeah, there's no monthly subscription. There's no you pay this setup fee or anything like that. You need to give them your billing information, I guess credit card information to set it up. You need to apply for permission and say, this is my use case. And then it's there to deploy and you have a choice of different models to use. And yeah, you can, I can't find where it is. I'm sorry, I can't find where it is in the user interface right now, but it shows you like daily how much you've used. And then it also makes some predictions based on how much you're using it. We expect it will cost this much this month.
And I have a capping. Does it stop me if I exceed €100, for example? So
That
if I'm silly and I lose my API key on GitHub.
Well, first of all, don't put your API key on GitHub, please. That goes in the git ignore file. Yeah, honestly, I don't know. That would be something we need to look at. Let me see if I can find that out, and I'll let you know later today about that. But I would imagine probably so. But it is trackable. But also with the model settings within the application. So if we look into my application properties that I set here, if I simply type in Spring AI here, we can see that, okay, there's a whole lot of options in here. You can see I have access to the Anthropic models as well. I've got all the Asia stuff. If I go through, I've got the Bedrock, which is from Amazon. This Cohere stuff, Llama, Titan, all kinds of models. We've got chat memory. I think this is the internal memory of it. I've also got the various embeddings that I can use, just tons and tons and tons of possibilities. But within the, like looking at the OpenAI stuff, which we've done, we can see that I can set some things about, for example, here I've got temperature and top P. This is to do with the relevance of, or the relevance in similarity searching and stuff like that. But I can also set, I can't see it right now, but I can set max tokens as well. So I can set token limits. But like I said earlier, if I say the output cannot be more than 500 tokens, that doesn't mean that the model thinks for a moment and says, okay, I can summarize all the things that I need to say into 500 words. What it actually does is just says what it's going to say. When it reaches that limit, that's the end of it, right? So
with the OpenAI API, I could pre-buy tokens. I pre-bought my tokens, and when one of my tests went amok, I just used them all up, and then it was finished. So I just want to avoid being broke because I made a problem.
Yeah, let's figure that out. I will take a look at that in the break, and we'll figure out by the end of the day whether that's possible. I'd imagine it must be, but yeah, I understand the concerns. But I think the main point of deploying in Europe is the DSGVO, right? If you're working with clients in Europe, they want to know that their data is secure and the organizations or let's say the servers on which their data is deployed is compliant, because the costs involved are astronomical, right? Yeah. Any further questions from anybody? Yes.
Does this model has some kind of caching mechanism? Because you said each token will be handled as if it's a new or new request.
How do you mean by caching? Do you mean like if I say, tell me more about that in my second query?
Yes, the same question again and again.
It's stateless, the model.
Okay.
So yeah, that's an interesting point. So for us using these models in our applications, there are further things that we need to consider, but the model itself is a stateless model. It's effectively a really, really smart algorithm. You might argue that's not an algorithm because an algorithm should give the same output for the same input, and an AI model doesn't always. But let's just kind of stretch the bounds of what this means here, because technology is changing fast. It's a thing that does a thing, right? So if we want to have some kind of additional context, that's something that we need to bake into our application logic, okay? If we want to be able to have an ongoing conversation with an AI model, then we need to handle the user input and the response from the model, save it somewhere in our application so that we can then pass that in as part of a system prompt, as additional information that the model can then use so it knows what we previously talked about. If we think about where this then gets more complicated is, let's say you're lonely and this conversation goes long into the night. Well, now we hit the maximum token limit on the input. We've got all this history of our conversation that started at 9 and now it's 2 in the morning, and you know, we've laughed, we've cried, but now that doesn't fit in the context window anymore. We need to think about how to handle that. So one of the things these AI large language models are great at is text summarization. So we can then, in our own application logic, perhaps have an asynchronous call to the model, which takes the conversation so far when it's reached a particular size and say, summarize this in such a way that it's useful to you to continue the conversation. We then get that returned. We save that somewhere else in our local application, and we can pass that in as additional data. So we still have the most recent part of the conversation for the model to use, but we've also got this summary of, well, we've been having this long conversation and this is what it means, if you see what I mean. Interestingly, sorry, one more point. Within the Asia OpenAI tool here, you can see that there's also the possibility for a playground where you can just kind of use the model. I tried this yesterday and it did not play. Tell me a joke. So yeah, it says it's early access playground. It doesn't seem to behave right now. I have played with this previously. It does work. It uses the browser's local storage to maintain context of the conversation, which is interesting. So yeah, you had another question.
Last question from my side. When you presented the model, it sounds quite deterministic. How come that the same input results in a different output on a state level?
Now you're asking the big question. Okay, the question is, how do you sometimes get a different output from the same input, right? And I've experienced this, and there are ways, once you start to play around with certain model settings, you can really make that happen more or less. So there is, I can't remember if it's temperature. No, it's the frequency penalty, perhaps. But there are certain settings you can use within the model which can you can force it to be more deterministic, or you can have it be more random. But the reason is that it's in a way, it's kind of a black box. It's not, but it is. So what's happening in the feed-forward neural network part of the model is that the parameters that are learned through the training process are applied to the embeddings that have now been subtly changed through the self-attention process, okay? So this learned knowledge, for want of a better word, is now applied to this input text that's been given positional encoding, contextual awareness, and this is where we see what might be termed emergent behavior or knowledge, for example. And it's an area of ongoing research. People are starting to think they know how this is happening, but there's no black and white answer right now. But my limited understanding of it is that the parameters in the feed-forward network, which are applied to the model, these are numerical values that are arrived at through the training process. The model has been trained on this vast volume of data, and they each have some kind of semantic meaning, which is then applied onto this embedding, this particular vector, right? But how is it different each time? I think it's a quirk of the way the models are made that we have the flexibility to say, give me just the same answer every time. Think about a use case of putting a model in an enterprise application. Let's say you're making an application for kids where you want a playful assistant that helps them with their homework that is also fun. You probably want a little bit more chaos in there. You want it to be a bit more random, a bit more playful. But let's say now you're making something where you need to really get the same answers to the same question. What is this? It is this, for example, that you can set that. So I would imagine when we use, let's say, for example, the ChatGPT web application, I would bet everybody in here has probably used it a lot already. they will have set that up in such a way that they've set these settings so that it appears human. If I asked you the same question on 5 different days, you might not give me the same answer, right? And this is the point. They are trying to emulate human language, human behavior, human responses, and a human won't always, most humans won't always give you the same answer, right? So that would be it's not the most precise answer, is it? I'm sorry, but I think that's probably the best I can do right now.
So there is some built-in uncertainty into the model, so it varies the answer.
Yeah, and we have control over it within the settings that we can set within our application as well.
Right.
Yeah.
And how they get tested these models? So there is one input and many outputs. So are there people who sit there and test a new model, or is there an AI who tests the model?
I think there's probably about 2 or more billion test guinea pigs right now using it on the internet, right? It's out there in the wild. However, I think what you're talking about is, Benedict is going to help me out here. There's a method of training where we have determined responses, right? Where we're looking for a specific response. I can't remember the name of it off the top of my head now.
Yeah, there are different parts of learning processes, like supervised and unsupervised learning.
That's what I'm talking about.
Yeah.
Okay.
There is semi-supervised learning where you have, I will talk about that in the first talk, where you have data that is not labeled, and database that is labeled, so you know what the model should say, and you can combine those two to create a large data set which is labeled, and then it knows what it should predict, and then can test on that and try to get to this direction to have the things it should.
Okay. Am I running over?
I was about to say, I hate to interrupt this discussion, but I'd suggest if you have any further questions for Ben, you can ask him privately so that the others can take a break.
Can I just finish up this one
Yeah,
point though, regarding the who's testing it and who's checking it. For us using it, which is kind of what we're about here today, right? How can we use it? How can we bring it into our application? That there is the functionality within the Spring AI framework that we can use an AI model to check the accuracy of an AI model's answer, right? Which, if you're using the same model twice, that's like asking me to check my own homework. Of course, I'm going to give myself an A, right? But you don't have to do it like that. You can say, all right, I'm using an OpenAI model here to generate my text. And within my unit tests, where I validate whether that's accurate, I'm going to have a model from Ollama deployed locally on my laptop, which I just use for testing. Or I'm going to deploy a model from Meta in the cloud somewhere, and I'm going to use that to validate the response from this model. So there is testing that we can do within our applications. But regarding the how do you know when the models are developed, yeah, it's the labeled responses was what I couldn't remember. So it's one thing to just let the model generate text and cool, it's made some text. That's awesome. Does it make sense? Kind of. But if we're looking for something specific, we will have a labeled data set. So this input should yield this output. And the simplest way to think about that is by having the model do image recognition. Here is a picture of a cat. If the model says it's a dog, the model's not good enough yet, because clearly that's a cat. Okay? All right. Thanks for listening, everybody. This was fun.